Generating high-quality textures for 3D assets has long been a bottleneck in content creation, whether for games, virtual reality, or digital twins. Traditionally, this task relied heavily on skilled artists, making it slow, expensive, and hard to scale. While recent advances in AI-driven texture generation have promised automation, two fundamental problems remain: multiview inconsistency and incomplete coverage of unseen or occluded regions. Existing multiview methods generate images from multiple angles and project them back onto the UV map. But when those views disagree, say one shows a red stripe, another a green one, the resulting texture becomes blurred or conflicting. Worse, areas hidden from all cameras are filled with generic, low-semantic content through simple extrapolation. On the flip side, UV-based methods try to generate textures directly in the UV space, but they lack strong geometric and semantic priors. Without access to 3D structure or view consistency, the results often fail to match the object's real-world logic. So what if we could combine the best of both worlds? That's exactly the idea behind MV2UV, a novel two-stage framework that treats multi-view images not as final projections, but as semantic prompts to guide high-fidelity texture generation on the UV map. Here is how it works. First, we use a multi-view diffusion model, like MV to generate a set of consistent, high-quality images from different viewpoints. Instead of immediately back-projecting these views, we treat them as image prompts for a second-stage diffusion model that generates the full UV texture map. This subtle shift is revolutionary. By using multi-view images as semantic guidance rather than literal input, our model learns to understand what should be where, not just copy pixels. It can resolve conflicts automatically, infer missing details, and generate textures that are both realistic and globally coherent. Now, the real magic lies in the cross-attention mechanism. How does the UV map know which part of the multi-view images to look at? The answer is geometry. Each pixel in the UV map corresponds to a specific 3D point on the mesh. So we use the 3D coordinates, the actual X, Y, Z positions of each pixel as positional encoding in the attention layers. This means, when the model is generating color for a pixel on the UV map, it dynamically attends to all multiview regions that share the same 3D coordinates. This geometric grounding ensures that attention is focused on meaningful, physically consistent regions, not arbitrary patches. And this leads to two major benefits. First, conflict resolution. Instead of averaging conflicting views or blurring them together, the model learns to resolve inconsistencies intelligently. It can choose the most plausible texture based on context, leading to sharper, more accurate results. Second, semantic inpainting. For UV regions that were never visible in any of the multiview images, like the back of a cup or the inside of a folded fabric, the model doesn't just fill them with noise or repetition. Instead, it pulls semantic cues from nearby visible regions. Because the attention is guided by 3D geometry, it knows that a pattern on the front of a chair should continue on the back, even if it's not directly visible. To make this work, we've redesigned the Diffusion UNet backbone based on stable Diffusion XL with three key components. First, we introduce reference attention, which extracts features from the multi-view images using a frozen reference network. These features are then injected into the UV generation process via a cross-attention layer. But crucially, we don't just use raw pixel features. We use geometric position encoding derived from 3D coordinates and normals. We apply a Fourier-based positional embedding to these coordinates to capture fine details, then pass them through a learnable convolutional encoder that builds a multi-scale feature pyramid. This pyramid aligns perfectly with the attention layers in the diffusion model, enabling precise, hierarchical geometric awareness. Second, we add a new UV self-attention module. Standard diffusion models struggle with UV maps because they're often split into disconnected islands, like the left and right arms of a humanoid. But in 3D space, those islands are adjacent. So we modify the self-attention mechanism to include the 3D position encoding in both queries and keys. This biases the model to attend to UV regions that are close in 3D space, even if they're far apart in 2D layout. The result? Seamless texture continuity across UV islands, especially important for complex shapes like dragons or furniture with joints. Finally, we keep the original self-attention and cross-attention modules frozen, preserving the rich 2D image priors learned during pre-training. But we add these new components in parallel, so the model can leverage both general image knowledge and geometric context. The result? A unified architecture that generates textures with unprecedented fidelity. We evaluated MV2UV on two large-scale datasets, GSO, Google Scanned Objects, and DTC, Digital Twin Catalog, covering everything from rigid furniture to deformable fabrics under diverse lighting. Quantitative results show a clear win. On both datasets, MV2UV achieves the best fit and KID scores, measures of visual similarity and distribution quality, performing state-of-the-art methods like Hunyuan 3D 2.1, MV and TEXGen. On GSO, it improves FID by 50.8 over UV-only methods. On DTC, it's 14.7 better. But numbers only tell part of the story. Qualitatively, the difference is striking. Compared to methods that directly project multi-view images, MV2UV avoids blurring and artifacts in inconsistent regions. And compared to UV-only approaches, it generates richer, more structured textures, especially in occluded areas. In ablation studies, we tested each component. Removing the geometric position encoding caused major artifacts. Without 3D guidance, the model couldn't align views properly. Removing reference attention led to poor semantic coherence, with textures that looked random or disconnected. And without UV self-attention, the model failed to maintain continuity across UV islands, especially on complex shapes. One limitation remains: textual elements. Due to resolution constraints and the inherent limitations of the VAE in Stable Diffusion XL, fine text details, like labels or logos, still suffer from blurring. This is an open challenge, but one we believe can be addressed with higher resolution encoders or specialized text-aware training. Still, MV2UV represents a significant leap forward. It bridges the gap between 2D image priors and 3D geometric structure. It treats multiview images not as inputs, but as semantic guides. It resolves conflicts not by averaging, but by reasoning. And it completes textures not by guessing, but by understanding. In short, MV2UV doesn't just generate textures, it understands them. This is not just a technical improvement. It's a paradigm shift in how we think about texture generation. From now on, the goal isn't just to project views or fill holes. It's to synthesize textures that are consistent, complete, and semantically grounded in the 3D world. And that's the future of AI-powered 3D content creation.